Hi everyone, my name is Morgan Shirley, and I am pleased to present some results on the nondeterministic and randomized Boolean hierarchies in communication complexity. This was joint work with Tony Pitassi at the University of Toronto and the IAS, and with Tom Watson at the University of Memphis. Here's an outline of this talk. Our main results involve studying Boolean hierarchies in communication complexity. It will be helpful to spend some time on background, definitions, and motivations first. Defined by Yao in 1979, communication complexity asks questions about the following setting. Two parties, Alice and Bob, each hold n-bit strings, which we'll call X and Y here, and their goal is to pass messages back and forth in order to compute some function of their strings. They are allowed unlimited computation power. The only metric on which they are measured is how many bits they need to communicate before they agree on the answer. The basic model of communication complexity is that the protocol that Alice and Bob use must be deterministic. That is, given fixed input strings, the communication between the two is always exactly the same. Studying the power and limitations of this model already leads to some interesting results in other areas of theoretical computer science. For example, in distributed computing and in monotone formula lower bounds. It is also interesting to study the model where Alice and Bob have access to a source of randomness and are only required to output the correct answer most of the time. Does this help Alice and Bob solve the problem while communicating less? This is analogous to the P versus BPP question in classical computation. But while it is reasonable to conjecture that randomness does not help more than a polynomial amount in Turing machines, so P may very well equal BPP, it is known that randomness does help quite a bit in communication. An important example of this is the equality function. Simply, does Alice's input equal Bob's? A simple argument about the properties of deterministic protocols shows that we need a linear amount of communication in the deterministic setting. The best possible protocol is for Alice to send her entire input to Bob, and for Bob to reply whether or not he has the same input. We can do much better in the randomized setting. Alice can randomly sample a prime number of length logarithmic in n, and send that prime as well as her input modulo that prime. If the inputs are equal, then Bob's input modulo the prime will always be the same as Alice's. If they are not equal, then with good probability their inputs modulo the prime will be different as well. We name classes of problems in communication complexity by analogy to classical complexity classes. Problems that are efficient for deterministic communication are in the class P with a CC superscript. Recall that in the worst case, problems have linear complexity in the length of the inputs, as Alice can simply send her entire input to Bob. Therefore, efficient can't mean polynomial. All problems have linear complexity, which is polynomial. Instead, by efficient here, we mean polylogarithmic in the length of the inputs. Polylogarithmic fortuitously also starts with a p, so that calling the class P makes some amount of sense. We define other communication classes by analog as well. The example we saw earlier shows that the equality problem is not in P, but is in BPP. In fact, because the protocol we gave never had false negatives, equality is in co-RP. Two other commonly studied classes are NP and P to the NP. In the NP model of communication, an all-knowing prover who can see the inputs announces a witness string, and the parties independently decide to accept or reject only seeing the witness string in their input. The cost of such a protocol is the length of the witness string. Note that there are some other ways to define non-deterministic communication that you might see in the literature, but all of these definitions turn out to be equivalent. In P to the NP communication, the parties can exchange bits of information just like in deterministic communication, but can also solve functions where they are charged the NP communication cost of that function. This is similar to the concept of an oracle query in Turing machines. These communication oracles come up quite a bit in this talk, so let me go into a bit more detail on them. Let's say Alice and Bob are trying to compute the output of a two-party function f, and they want to do so using polylogarithmic communication in the model p to the np. If they are able to do so, then f is in p to the np. As a part of this protocol, they are able to compute the output to a different two-party function g that has polylogarithmic np communication complexity in the following way. Each one writes down an input to g privately. This input to g can depend on their input to f and on the communication that has occurred thus far. Then they get the output from g, and they can hopefully use this to help them solve f. The cost that this adds to the overall protocol is the NP cost of G. Communication complexity classes such as these may seem a bit esoteric, but it turns out that they can have some interesting consequences. If we take these oracle classes to their logical conclusion, we get a class that corresponds to the polynomial hierarchy. And this class has deep ties to matrix rigidity and static data structures. Unfortunately, we don't even know how to think about the second level of the communication complexity polynomial hierarchy, let alone the whole thing. This brings us to a big open problem in communication complexity. What is the relationship between BPP and P to the NP? We know that P to the NP can solve problems efficiently that take linear time in BPP. One example is the set disjointness function. If we allow Alice and Bob to solve partial functions, that is, they have a promise on their input, BPP can do much better than P to the NP on certain functions. So the classes are incomparable in this setting. This doesn't say anything about BPP versus P to the NP for total functions, though. It's common in communication complexity to consider both the case where partial functions are allowed and the case where total functions are required. When solving partial functions, protocols are allowed to break the rules on inputs not in the support. So in this case, the BPP protocol must be correct with probability bounded away from 50% on the inputs in the support, but can answer incorrectly or with probabilities close to 50% otherwise. An example where a difference between the total function setting and the partial function setting has been shown to hold is P versus NP intersect co-NP. A well-known communication complexity result shows that these classes are the same for total functions, but they can be exponentially separated if partial functions are allowed. Remember this example as it will come up later. One approach to making progress on the BPP versus P to the NP question that I'd like to highlight is to first solve BPP versus P to the RP, where P to the RP is defined like P to the NP, except that the oracle class is functions that have randomized protocols with one-sided error. If these are equal for total functions, then BPP is strictly contained in P to the NP, as we already know that P to the RP is strictly contained in P to the NP. Up until recently, many researchers thought that, in fact, BPP was equal to P to the EQ for total functions. In P to the EQ, the function that is queried must be the equality function, and the cost for doing so is 1. This seemed reasonable because every randomized protocol known at the time could be written using equality oracle calls. Chattopadhyay, Levitt, and Vinyals recently disproved this conjecture. In fact, they show an infinite hierarchy of stronger and stronger functions with one-sided randomness, so these functions are in co-RP, such that each function cannot be solved with oracle access to any of the previous functions. Our contribution to this area is to study what happens when, instead of changing the strength of the oracle, we change the number of times that the oracle is allowed to be called. Specifically, we study the randomized Boolean hierarchy in communication complexity. Let me first define the nondeterministic Boolean hierarchy. Let Q be a constant. The class P to the NPQ parallel, I'm sorry that this is a bit of a mouthful to say, contains problems which have efficient P to the NP style protocols with the constraint that we are only allowed to have at most Q NP oracle calls, and that these calls must be made non-adaptively. That is, the queries must not depend on the answers to previous queries. You can think of this as the queries being made in parallel. This is a natural way to study the power of adding more NP oracle calls. Unfortunately, these rather well-motivated classes are hard to reason about without studying a slightly different set of classes that is traditionally called the Boolean hierarchy. We call it the Nondeterministic Boolean hierarchy to differentiate it from the Randomized Boolean hierarchy that I'll define in a moment. The first level of the hierarchy has classes NP1 and co-NP1, which are equivalent to NP and co-NP respectively. The Qth level has classes NPQ and co-NPQ. Protocols in these classes look like this. We have QNP problems, and we ask whether an odd or even number of them would return true on the inputs. For protocols in NPQ, if the answer is odd, we return true, and if the answer is even, we return false. For co-NPQ, reverse these. This looks a little weird. Why should we think of taking the parity of QNP functions? In fact, there are a number of ways to define the nondeterministic Boolean hierarchy that have been studied in both classical complexity and communication complexity. And it turns out these other ways are equivalent to this odd or even construction. I'm not going to define these other ways here, but if you're interested, here are a couple of references. We use the parity definition because it happens to be pretty easy to think about in communication complexity. The other definitions more clearly capture the idea of bounding the number of calls to an NP oracle, but are unfortunately less clean. In communication complexity, the nondeterministic Boolean hierarchy is intertwined with the set of classes P to the NPQ parallel that we defined earlier. NPQ is strictly contained in P to the NPQ parallel, which in turn is strictly contained in NPQ plus 1. In fact, previous work almost entirely characterized the relationships between classes in the communication nondeterministic Boolean hierarchy. Only one question was left open. Is P to the NPQ parallel strictly contained in NPQ plus 1 intersect co-NPQ plus 1? It was known that the containment is true, but not whether the classes are different. Note that if we take Q equals 0, this is simply the P versus NP intersect co-NP problem from earlier. If you'll recall, the classes are equivalent if we only consider total functions, but they are different if partial functions are allowed. One of our results is that the same holds for any constant Q. An easy modification is to exchange NP with RP, the set of problems with efficient randomized algorithms with no false positives. This is the Randomized Boolean hierarchy. The Turing machine version of this hierarchy has been studied, but not the communication complexity version. This hierarchy is a natural way to model more RP calls, which you'll recall is our goal. Here's some examples of functions in various levels of the Randomized Boolean hierarchy. We already saw that equality was in co-RP, and so the negation of equality, non-equality, is in RP. Both of these are in the first level of the hierarchy. Let me define a function that I'll call parity of Q non-equalities. Alice's and Bob's input are each divided into Q blocks, x1 through xq, and y1 through yq. Parity of Q non-equalities returns true if there are an odd number of I such that xi is not equal to yi. This is pretty clearly in RPQ. Simply negate this to get negated parity of Q non-equalities. This function returns true if there are an even number of I such that xi is not equal to yi. This negated parity of Q non-equalities function is in co-RPQ. Our main contribution is to relate the randomized Boolean hierarchy to the nondeterministic Boolean hierarchy. It turns out that these are intertwined in such a way that shows that the randomized Boolean hierarchy does not collapse. That is, more RP calls help compute more functions. Also, earlier I mentioned that we resolved an open problem concerning classes in the nondeterministic Boolean hierarchy. We also showed the same result for the randomized Boolean hierarchy. Together, these results completely resolve questions about the separations between classes in both Boolean hierarchies. For the rest of the time that I have, I'd like to talk a bit about the ideas behind the proofs in our paper. First, we proved that co-RPQ can efficiently solve problems that NPQ can't. The function that we use to separate these is the negated parity of Q non-equalities function from earlier. Recall that this function is in co-RPQ by the fact that the negation of the equality function is in RP. We prove that it isn't in NPQ by a fairly direct combinatorial argument. I won't go into the details, but intuitively this result makes sense. Non-equality is in NP, so an NPQ protocol can return true when an odd number of blocks are different very easily, but equality is not in NP, so the negated problem should be difficult for NPQ. This result proves that the randomized Boolean hierarchy is infinite, because RPQ is contained in NPQ. And so co-RPQ is not equal to RPQ for any constant Q, and therefore the hierarchy does not collapse. The resolution of the question of P to the NPQ parallel versus NPQ plus 1 intersect co-NPQ plus 1 is more complicated to prove. For total functions, the equality is fairly easy to show, and it is constructive. If you give me efficient NPQ plus 1 and co-NPQ plus 1 protocols for a function, I can give you a P to the NPQ parallel protocol. If we replace NP with RP here, the construction remains the same. The separation in the partial function case is much more involved. It involves proving a query to communication lifting theorem for NPQ and P to the NPQ parallel. Query to communication lifting is when the hardness of a function's decision tree complexity is lifted to show the hardness of a related communication function. We give a partial function that is hard for a model of decision trees that is analogous to P to the NPQ parallel, and show how that gives a related communication partial function that is hard for P to the NPQ parallel itself. We also show that the related function is easy for both RPQ plus 1 and co-RPQ plus 1, which gives the desired separation for both the nondeterministic and randomized hierarchies. For those of you who are familiar with lifting theorems, I'll quickly give a couple of details on ours. Both of our lifting theorems use the index gadget with a size of n to the 20, which means that both of them incur a logarithmic penalty in the simulation. Our NPQ lifting theorem is based on the Guskamath, Pitassi, and Watson lifting theorem for P to the NP. Used out of the box, their lifting theorem would not preserve the constant Q in NPQ. We make modifications to ensure that this Q remains the same after the lifting takes place. Our P to the NPQ parallel lifting theorem essentially glues together the deterministic lifting theorem of Rosen-Mackenzie to our NPQ lifting theorem. This result is a bit more straightforward than the proof of correctness for the NPQ lifting theorem, but still requires some work to make sure that the deterministic and NPQ lifting theorems play nicely together. To conclude, let me give you some open problems. We pretty much completely resolved the structure of both the randomized and nondeterministic Boolean hierarchies, but there is still other work that can be done. Not much is known about relationships between other natural communication classes and classes at high levels of the hierarchies. Another thing that might be useful is a query to communication lifting theorem for classes in the randomized Boolean hierarchy. In our paper, we only needed lifting for classes in the nondeterministic Boolean hierarchy. Boolean hierarchies represent protocols with a constant number of oracle calls. What if we still bound the number of calls, but by a super constant amount? Finally, let me remind you of the big open questions of BPP versus P to the RP and BPP versus P to the NP. Thanks for watching, and have a great day.